non-Fermi, really non-Fermi liquids, in fact, although I will say something about Fermi liquids as well. So this is work that I did with my collaborators, Ryan Fongren and Sento. So let me begin by asking a very basic question: what is a metal? Okay, so I mean, an example of a metal is a non-interacting gas of electrons. So we have electrons, but they don't interact at all. So all they do is they fill up some Fermi C, and then so you have single particle states, and then at zero temperature you have some set of single particle states which are occupied, and then some set that are unoccupied, and the Fermi surface, of course, is the boundary between the occupied and unoccupied states. And the low energy excitations of this state are the electrons or the holes near the Fermi surface. So that's a non-interacting electron gas. But then we can imagine, of course, switching on the interactions, and then we have this famous Landau Fermi liquid theory. So in a Landau Fermi liquid, because you have interactions, the single particle states are not well defined anymore. If you have a particle at some generic momentum, it will just rapidly scatter. But near the Fermi surface, it turns out that you still have these dressed quasi-particle excitations, which are well defined. In fact, they have a lifetime that goes as 1 over E squared, where E is the excitation energy. So very close to the Fermi surface, these have very long lifetimes, and these quasi-particles describe the dynamics of the system at low temperatures. And so one consequence of these quasi-particles is that the system will thermalize very slowly, because the only way you can thermalize is by scattering the quasi-particles, but that can happen only very slowly because of this, almost by definition, a quasi-particle for lifetime is very long. Okay, but so that is a classic story, but now we want to go further. We know, a very important thing about a Fermi liquid is Luttinger's theorem. Luttinger's theorem tells us that the volume enclosed by the Fermi surface is unmodified by the interaction. So you switch on the interactions, the Fermi surface may get renormalized, but the total volume enclosed will always remain the same. That's a very non-trivial result. It's a property of Fermi liquid theory. So now we want to go beyond Fermi liquids, because we know that there are metallic systems that are not Fermi liquids. And so often these metallic systems, they don't have any well-defined quasi-particle excitations at low energy. So the question arises, how do we describe the system if not by quasi-particles? So, and then one consequence of the absence of quasi-particles is that the system could thermalize much more rapidly than a Fermi liquid. Okay, there are a lot of questions we can ask about non-Fermi liquids. First of all, what do we mean by Fermi surface in this system? I mean, it's not associated, it's not, in Fermi liquids, it was associated with the locus where the quasi-particles have a long lifetime, but in a non-Fermi liquid, there are no quasi-particles. So what do we even mean by Fermi surface? Is it still a well-defined concept in a non-Fermi liquid metallic state? Sometimes people would say, if you look at some electron Green's function or something, it would have maybe some non-analyticity at some surface in the momentum space, but it doesn't feel like a very fundamental definition. I would like something more fundamental than that. So what do we mean by a Fermi surface? And okay, if there is, supposing that there is a Fermi surface, what is the significance of a volume enclosed by the Fermi surface? We know that in a Fermi liquid, you have Luttinger's theorem, but what happens in a non-Fermi liquid? Is it still the case that the volume inside the Fermi surface is the same? So does it obey Luttinger's theorem or not? These are some questions that I would like to understand about non-Fermi liquids. And let me also pose some questions in a different way, although they will end up being actually related. So we know that in kinetic matter systems, we know microscopically always what our degrees of freedom are. Usually there's some system of electrons. So that's in the UV microscopically. And then we know that in the IR, you can have many different emergent behavior: insulated state, metallic state, non-Fermi liquid metallic state. And in the IR description might seemingly have very little connection to the UV degrees of freedom. And it's very difficult to predict what the emergent behavior is going to be just from knowing the microscopic Hamiltonian. So we would like some way, at least, to say something about the IR physics by knowing something about the UV, at least partially. And so one thing that we can say is that if the UV has some symmetry, then the IR must also have that symmetry, at least unless it's spontaneously broken. Because spontaneously broken symmetries themselves have signatures such as Goldstone modes. But in any case, certainly if the symmetry is not spontaneously broken, then whatever the symmetry is in the UV, the IR theory must have that symmetry as well. So that's already a connection we can draw between the UV and the IR. And so in this talk, I'm going to assume the following symmetry group, which is very physical. I have lattice translation symmetry, and I have some charge conservation symmetry, so U1. So it's a symmetry I will assume. But the interesting about this symmetry is that once we have this symmetry, we can also define this thing called the fill-in, which is a microscopic total U1 charge per unit cell of the translation symmetry. So, okay, that's a property that we can define microscopically. But the question is, how does that relate to properties of the IR theory? That's kind of the question I want to pose. So we can ask, in a given microscopic fill-in, what IR theories are consistent with that? And so let's consider some simple examples. Of course, the simplest IR theory is just an atomic insulator. So in this case, the electrons kind of live in clouds around the ions, and the clouds don't talk to each other. So in this case, because the number of electrons in each cloud must be an integer, we deduce that the fill-in is an integer. And the fill-in is also an integer in any band insulator. Even there are band insulators that cannot be smoothly connected to atomic insulators. Churn insulators, for example, cannot be connected to atomic insulators. But in any case, it's still true that in a band insulator, the fill-in is always an integer, which you can determine just by state counting the number of states in the band. So how do we get fractional fill-in? Well, okay, of course, we can have a metallic system. In particular, if we have a band metal, then you have some band which is partially filled. And then in that case, the fill-in does not have to be an integer. And so if you count the number of states contained inside the Fermi surface, you will see that the fill-in is directly related to the volume enclosed by the Fermi surface. And then so in a non-interacting system that comes from state counting, in a interacting system, we know where we have Luttinger's theorem, so this formula is still true with interactions, as long as the state is still a Fermi liquid. Oh, and by the way, the fill-in is determined by volume of the Fermi surface only mod 1, because you can always add a fully filled band, so that's why it's mod 1 here. And then, so these are particular examples, but there's a more general theorem that has been stated by Lieb-Schultz-Mattis and in a more systematic way by Oshikawa and Hastings. And it tells you that if you have a system which is microscopic fill-in, which is not an integer, so mu is not 0, not 1, then this system, the IR theory, cannot be gapped unless it has ground state degeneracy on the torus. So something non-trivial has to happen if the microscopic fill-in is not an integer. Either the system is gapless, has gapless excitations, or the second option is it's topologically ordered, because we know the topologically ordered states have ground state degeneracy on the torus. So these are the options, but that still leaves a lot of uncertainty. There are many, for example, different gapless theories, so which one are compatible with a particular fill-in? So these are the kind of questions I want to answer. Given that the fill-in is not an integer, of course, if it's an integer, then the system could just be a trivial insulator, as I mentioned. But if a fill-in is not an integer, then what exactly does this imply about the IR theory? So that is another question that I want to answer. So that's kind of the introduction. And so now I want to return to Fermi liquids. Eventually, I want to make much more general statements, but let me return to Fermi liquids for the moment and sort of re-express what stuff that we maybe already knew about Fermi liquids, but in a new way. Maybe you could call it a more modern way, which I think will be very illuminating and will demonstrate how we can go further beyond Fermi liquids. Okay, so a brief history of Fermi liquids. Of course, Landau told us that we should take a non-interacting gas and then adiabatically centrifuge on interactions. But that's generally not really the way that people think about it these days. Normally, the more modern way to think about it is that the Fermi liquid is an example of a renormalization group fixed point. So whatever the UV degrees of freedom is, in the IR, it should flow to some renormalization fixed point, and Fermi liquid is an example of a renormalization fixed point that it could flow to. And so it's a stable fixed point if you forget about superconductivity. And so famously, this was discussed in this review article by Shankar and references varying. But there's also a very interesting thing about this renormalization group fixed point that describes Fermi liquid theory. It has a very large emergent symmetry group. So whenever you have some UV theory with some symmetry, the IR theory could, in principle, have a much larger symmetry. So that's what we call emergent symmetries. And in fact, the Fermi liquid has a very large emergent symmetry. The reason for that is if you think about the Hamiltonian for the Fermi liquid fixed point, which is just basically the non-interacting Hamiltonian plus these Landau interaction terms, and these are the only terms that are not irrelevant. Then you see that it commutes with the nk for all k. So what you conclude is that in fact the charge at every point of a Fermi surface is separately conserved. So instead of microscopically, we just had a global U1 charge conservation symmetry, but actually in the IR, in this fixed point, the charge at every single point on the Fermi surface is separately conserved. So that's a very extremely large emergent symmetry group. So that's a property of a Fermi liquid. So I think Haldane maybe was the first person to point this out, but you can't say that it's really been used very much after that, I think. But in my talk, this emergent symmetry group is really going to be the fundamental thing that's going to allow me to make statements about Fermi liquids. So it will play an essential role. So I want to explain how that works, but in order to make things simpler, I want to, before I consider some Fermi liquid in 2 or higher dimensions, I want to consider a one-dimensional system. So I would say a one-dimensional Fermi liquid, except that technically there is no Fermi liquids in 1D, where you have Luttinger liquids instead of Fermi liquids. Actually, that distinction won't be very important for what I'm saying, so you don't need to worry too much about that. Anyway, so I'm going to talk about a 1D Luttinger liquid, and I'm going to talk about it from a particular point of view, as you'll see, as in particular emphasizing the emergent symmetry. Okay, Luttinger liquid, instead of a Fermi surface, because you're in 1D, you just have a Fermi points. So we'll call these KL and KR. If you like, you can think about the non-interacting limit, in which case you just have a gas of electrons, and then you have some dispersion relation, and then you fill the states below the chemical potential. And KL and KR, as always, are the boundaries between the filled states and the empty states. So the Luttinger liquid has an emergent symmetry. It's maybe not as large as the Fermi liquid in higher dimensions, but it's still larger than the microscopic symmetry. The emergent symmetry of the Luttinger liquid basically is U1 times U1. And this is basically saying that the charge at each of the 2 Fermi points is separately conserved. So microscopically, you just have the total charge conservation, but in the IR, you have the charge at both the left and right moving Fermi points is separately conserved. And then another interesting thing about this emergent symmetry, it has what people call the axial anomaly. So that basically says that you apply an electric field. So without electric field, then as I said, the charge of the left and right moving Fermi points will be separately conserved. But if you apply an electric field, that's no longer the case. So if you write down the continuity equation for the left and right moving currents, it's violated by there's a non-zero right-hand side in the presence of an electric field. So at least in the non-interaction limit, it's kind of easy to understand why this should be true, because if we have apply an electric field, it will induce a flow of electrons in momentum space, so kind of flow in the direction of electric field. And so if they flow in this way, then you get charge accumulated at KR, and you get charge deficit at KL. So that's the reason for this anomaly, at least in the non-interacting limit. It turns out that the same thing is still true once you switch on the interaction, so you have this anomaly. So this axial anomaly is an example of what people call a Hooft anomaly. So let me just say a few words about that. So the Hooft anomaly generally means that if you apply a background gauge field, that the charge is not conserved anymore. So let's describe by these equations here, for example, for the axial anomaly. So a Hooft anomaly is a kinematic property. It's not a dynamical property. So what do I mean by that? If you're a field theorist, you would say that the source of the anomaly is the measure of a path integral. Like the path integral measure is not invariant under gauge transformations. But if you're not a field theorist, you can maybe say it in a different way. It's that the anomaly, the source of the anomaly comes from just the way that the symmetry acts on the Hilbert space. So it doesn't come from the Hamiltonian. The Hamiltonian is kind of irrelevant for this anomaly. It only comes from the way that the symmetry acts on the Hilbert space. That's what I mean by kinematic property. The Hamiltonian could be anything, and you would still have the same anomaly. And then also, Hooft anomaly, it's famously related to symmetry-protected topological phases in one higher dimension. So there's this bulk boundary correspondence. And then a related property is that the coefficient of the Hooft anomaly is quantized. So if you look at this anomaly equation and then you try to deform this equation, you would find that it's not possible unless you could replace the coefficient here by a different integer. But if it's not an integer, then the equation would be inconsistent. So you have this quantization of the anomaly coefficient. So you can't continuously deform the anomaly. So okay, so that's a brief review of the Hooft anomalies. But let's get back to the Luttinger liquid. And in particular, what I want to argue is that this axial anomaly actually implies Luttinger's theorem for the 1D Luttinger liquid. So I think it's well known that the 1D Luttinger liquid obeys Luttinger's theorem. And I think to some extent the argument that I'm going to give is also well known, but I really want to emphasize the sense in which it's coming from the anomaly. Okay, so let's talk about the IR theory for the Luttinger liquid. And so remember that whatever the microscopic symmetries are, they have to somehow act in the IR theory, assuming that it's not spontaneously broken. So in particular, let's assume that we have microscopically a continuous translation symmetry. It's just to make things easier, I could do this argument for a discrete microscopic translation symmetry if I wanted to. So if you have a microscopic continuous translation symmetry, it means you have a momentum operator. And then we have to say, how does that momentum operator act in the IR theory? And basically it has to act like this, because if you have some number of particles at a right moving Fermi point and then some number at the left moving Fermi point, and the total momentum is just given by the sum here. So that's how momentum acts in the IR theory. So these NL and NR are the generators of the emergent symmetry. So NL is the number of left moving particles, and similarly for NR. And then we can recall that we have this axial anomaly equation. So if I integrate this over all of space, I can find how the density of left moving and right moving charges changes. So NL dot is the time derivative of NL, and little NL is the density of left moving charge. So the time derivative of density is non-zero in the presence of electric field. That's what the anomaly tells us. But then because we know that the momentum density is related to the charge density by this equation, we can now conclude that the rate of change of momentum density takes this form. But then we also know, so that's in the IR theory, but we also know microscopically the rate of change of momentum density has to be equal to the electric field times the charge density, because that's the force density that's experienced by the system. So therefore, by equating these two formulas for P dot, we get this relation between the microscopic charge density and Kr minus Kl, which is basically the one-dimensional volume enclosed by the Fermi surface. So this indeed is Luttinger's theorem for the 1D Luttinger liquid. And so all I needed to use here was the emergent symmetry and the anomaly. So now let's try and do something similar in higher dimensions. So of course, Luttinger's theorem for Fermi liquids was originally proven in a way that was perturbative in interaction strength. But then Oshikawa came up with his amazing non-perturbative argument by flux spreading. And so I'm actually going to give a new non-perturbative argument. It'll look quite different from the Oshikawa argument. And as far as I know, it's new. And I'm going to emphasize in particular that it will be phrased just in terms of the emergent symmetry and the anomaly of the Fermi liquid. Okay, so let's talk about to keep things simple as much as possible, a two-dimensional Fermi liquid. And then, so first of all, I need to identify what is the emergent symmetry group of a 2D Fermi liquid. So as I said before, the charge is conserved at each point of a Fermi surface separately, which is kind of why there's a large emergent symmetry group. Let me just be a bit more precise about what the emergent symmetry group is. You might naively say it's just U1 to infinity, so there would just be a U1 for each point of a Fermi surface, but it's not actually correct. Because there isn't a quantized charge associated with each point of a Fermi surface. What you have is a conserved charge density. And by charge density, I mean charge density with respect to theta. So theta is some coordinate that parameterizes a Fermi surface. And so to get the total charge on the Fermi surface, you would integrate this n of theta over d theta. So it's a charge density in momentum space, so linear charge density of a Fermi in momentum space. So this basically these n of theta operators are conserved, and they're going to be the generators of the emergent symmetry. So we can write a general element of emergent symmetry by integrating the n of theta against some general test function and taking the exponential. And then for the test this function f, we'll take it to be any smooth function. We don't want to allow too many singularities in f, because that would, if we did that, we would get operations that depend very sensitively on the kind of the short momentum cutoff, which we don't want. So we're going to require that the function f be smooth, and then we integrate that against a general against the density operator, and that's how we get a general element of the symmetry group. And there's some slight subtlety, because the total charge is quantized. It means that f of theta is actually defined only mod 2 pi. So that kind of tells us what the emergent symmetry group of a 2D Fermi liquid is. It's the group of smooth functions from the circle into U1. So the circle just represents a Fermi surface here. That's topologically, at least it's a circle. And then so because we have this identification of f of theta is f of theta plus 2 pi, that's why the target is U1. And so the emergent symmetry group is a group of smooth functions from the circle into U1. And mathematicians have a name for this. They call it the loop group of U1. And so I'm going to write it as LU1. So LU1 is the emergent symmetry group of a 2D Fermi liquid. So that's the emergent symmetry. Now let me talk about the anomaly of the 2D Fermi liquid. That's kind of the other ingredient that I need. So I could write it as a valuation of the continuity equation, in the same way that I did in the 1D case, but it ends up being a bit complicated. I may talk about that towards the end if I have time. But it's actually a simpler way to understand the anomaly in 2D Fermi liquid, and it's as follows. So I'm going to consider applying a background magnetic flux. So I apply some magnetic field to the system in some spatially dependent way, such that if I integrate the total magnetic field over space, then I get 2 pi. So it's a 1 flux quantum. So I'm going to take the magnetic field, I'm going to take these 2 pi flux to be very spread out, so that the magnetic field locally is very small. That ensures that I'm really probing the IR theory, because it's a long wavelength excitation. And so the point is that once I create this 2 pi magnetic flux configuration, it turns out that the symmetry, the emergent symmetry of the theory will act projectively on this 2 pi flux configuration. And that will be the signature of the anomaly. So let's see exactly how it comes about for the Fermi liquid. So it turns out, what I mean, so remember that the emergent symmetry is generated by this linear density operators n of theta. So what I mean by projectively is that, acting projectively is that, in the presence of this 2 pi flux, these density operators which previously commuted with each other now will no longer commute. They have a non-zero commutator given by this equation. So delta prime here is the derivative of the Dirac delta function. So perhaps this looks familiar because it's actually the same equation that you have for the commutator of the density operators of a chiral fermion in 1D. So chiral fermion in 1D has this, if you look at the local density, it has this non-trivial commutator structure. Okay, so that's not a coincidence. I mean, there is a way to relate this Fermi liquid with 2 pi magnetic flux to some sense to a 1D chiral fermion. The argument is as follows. So because this is a very long wavelength perturbation, that's the it's a long wavelength field configuration. This is the context in which we're allowed to apply the semi-classical theory of electron transport. So in the semi-classical theory, we remember that we have this equation of motion. So the derivative of k is given by this v cross b in the presence of a magnetic field. And so this tells you that that there's a flow of particles along the contours of constant energy in momentum space. So in particular, the Fermi surface is a contour of constant energy, so there's a flow of particles along the Fermi surface. And it's a chiral flow because it goes only in one direction, set by the sign of the magnetic field. So basically, what we see is that in the presence of this 2 pi, in the presence of magnetic field, you effectively get this chiral fermion in momentum space. So that's kind of intuitively the reason why we get this same commutated structure as for a chiral fermion. Now, admittedly, this argument is a bit hand-wavy, not too precise, but we can derive this commutator more precisely in the 2D Fermi liquid. Basically, if you take the semi-classical theory and evaluate the Poisson bracket of these density operators, because the semi-classical theory, is a Hamiltonian theory. You can evaluate Poisson brackets. You find that a Poisson bracket exactly gives you this on the right-hand side. And then, of course, in the fully quantum theory of a Poisson bracket.
So the left side of this slide and the lower bottom and the lower right side seem to be independent of the Hamiltonian, right? And the upper right seems to depend on the equation of motion and therefore the Hamiltonian. Is this right?
Yeah, I mean, that's right. I mean, this is an example of a Hooft anomaly. So indeed, the Hooft anomaly is a property of the Hilbert space, not of a Hamiltonian. I mean.
So what is the significance of the upper right part of the slide?
I mean, it tells you. I mean, it tells you that you have this chiral fermion. So I mean, there's kind of some restriction of what the low energy theory could be, given that you have this type of phenomenon. Like for example, if you're on the boundary of a quantum Hall state, which is the other case where you have this, this symmetry, this commutator structure, that it can't be just a regular non-chiral fermion. It has to be a chiral fermion, right? So there's some restriction on the nature of the low energy theory that comes from the symmetry structure. And so it's kind of the same thing here. You basically needed to have something like a chiral fermion because of its symmetry structure.
I see.
Maybe another comment is that E of k is not really the Hamiltonian. It's just the function that defines where the Fermi surface is. That's all. It's just a geometric statement of where the curve is.
Oh, yeah. So it's really independent of what E of k is.
In the end, yes.
That's true. I mean, you indeed get a chiral fermion no matter what E of k is. I mean,
thank you. That clarifies it.
Yeah.
Yeah, there's a related question. If the Fermi surface is not circular, has some very strange shape, then this commutation relation may be modified because theta will not have that meaning.
I should clarify, maybe I should have said this. Theta is not actually theta is any coordinate that parameterizes the Fermi surface. It doesn't actually have to be like the angle. It doesn't really matter. In fact, if you think about like how does equation transform under reparameterization of a Fermi surface, it's actually invariant. So it doesn't really matter what coordinate system you use to describe the Fermi surface.
Right, but for example, if you have an open Fermi surface, would the commutation relation be modified in any way?
No, it's not modified. Although then I guess you kind of have to use a slightly different variables because you have to say like which segment of a Fermi surface you're on. But locally, I mean, this commutator is a local property, so that's not changed.
But if a Fermi velocity depends on theta, whether there is a change.
Well, this equation is independent of a Fermi velocity. So
I mean, commutation relation. So we're not depend on the Fermi velocity.
Yeah, that's right. And that goes back to this statement. The Fermi velocity is kind of a property of a Hamiltonian, but this equation is independent of a Hamiltonian.
But the equation motion seems to depend on Fermi velocity. That's a partial E, partial K is a Fermi velocity.
Yes. So the equation of motion is really the dynamics of a system, and that indeed will depend on a Hamiltonian. But this commutator is a more fundamental property that is independent of Hamiltonian.
Okay, thank you.
Actually, it's also a similar question here. So is it important that on the left-hand side, you talk about a 2-pi flux? Like on the right side, there is a B, but B never really show up.
That's kind of a subtlety. You don't really see, from this point of view, like the thing is that a chiral fermion can have like, in general, depending on like, the central charge, it could have like a different, coefficient in front of here, right?
Yeah.
I mean, that's kind of something you don't see at just at a purely classical level. So that's kind of why in this semi-classical picture, you don't really see at least at the level of equations of motion, you don't really see exactly what this coefficient should be. But if you actually evaluate this Poisson bracket carefully, then you'll find that a 2-pi magnetic flux gives exactly this coefficient.
And can I talk about a fraction of 2-pi flux? Does it even make sense?
It's kind of not really a local excitation now, right? Because you can detect that far away. So yeah. I don't think that you would want to ask for what the.
So maybe in short, I could say that if I'm talking about a fraction of a 2-pi flux, I wouldn't have a local commutation relation between the ends. Is that fair to say that? It's unexpected to have a nice algebra.
Right, I would say that I'm not sure the commutator is even well defined. I think when you talk about a symmetry acting projectively on excitation, you kind of really want it to be local excitation, I would say.
Okay.
Okay, so yeah, any more questions on that? Okay, so let me move on. So this commutator is going to be the key to obtaining Luttinger's theorem, as we'll see. So yes, in fact, that's my slide now. So as we argued before in the 1D case, basically we want to do some matching between the IR theory and the UV properties. So let's temporarily go back to the UV. So microscopically, we have this translation symmetry. I'm considering discrete translation symmetry here. And then we can ask, in the presence of 2 pi magnetic flux, this translation symmetry also will be projective. And then we can see why, because, well, this is a kind of not a rigorous argument, but if you imagine a 2 pi flux, and then you act on it with this Tx, Ty, Tx inverse, Ty inverse, it's kind of like you're moving it around a unit cell. So then you should get a phase factor associated with how much charge is in the unit cell. And the charge in the unit cell is filling, nu. And so you get this phase factor e to the 2 pi I nu. Admittedly, it's not a very rigorous argument, because I told you before, 2 pi flux is supposed to be like very spread out. But anyway, you can, if you're careful enough, you can construct a more careful argument. It turns out that this formula is still correct. So microscopically, you have the commutator translations with this form in the presence of magnetic flux. And then, so we go back to the IR theory. Okay, the translation symmetry is assumed to not be spontaneously broken, so it has to act on the IR theory in some way. And so in particular, it's going to act in this way. So it's expressed in terms of these NF thetas that I introduced previously. So this K is basically the K alpha theta traces out the momentum of the Fermi surface as a function of theta. And so if you have a certain amount of charge at some location theta, then you know, the momentum contribution is going to be proportional to K and proportional to the amount of charge there. So that's basically why you get this formula for the translation operator. So this is how translation acts in the IR theory. And now we can go back to this 2 pi flux. And so I told you that you have this commutator at the NF thetas, but then because the translation operator T is expressed in terms of the NF thetas, now we can compute the commutator of translations. So you will find this particular formula. So you find that the commutator is proportional to e to the I df, where df is the volume enclosed by the Fermi surface. Well, you can kind of see why this happens, because you have this derivative of delta function, then you integrate by parts, you're going to get something like this. So the commutator translations in the IR theory is proportional to the volume enclosed by the Fermi surface. On the other hand, microscopically, it's proportional to the filling. So therefore, you know, we equate these two equations, and we get the relation between the volume enclosed by the Fermi surface and the filling. And that indeed is Luttinger's theorem for a 2D Fermi. And so the interesting thing about this argument is that the only thing we used was the emergent symmetry structure and the Hooft anomaly. That's the only ingredients that we required.
Question?
Yes.
So suppose some of the symmetries is spontaneously broken. It may be implemented non-linearly in the L theory. In that case, can I still make some statement?
I'm not sure what you mean by non-linearly.
For example, in a superfluid, the U1 symmetry is spontaneously broken, and we write the Lagrangian as d theta squared times the stiffness. The U1 symmetry now acts as it sends theta to theta plus a number.
Yeah, but I mean, the unitary operator in plane symmetry is still a linear operator. I'm not sure I understand. I mean, you can. I mean, if you consider the you know, the whole IR theory, that is all the different symmetry breaking ground states, and the symmetry acts in that theory still. And so you can actually still apply this argument in that case. You know, you consider the whole IR theory, including all the symmetry breaking ground states, and then you consider how does the symmetry act on that IR theory, and what is its anomaly. And I mean, the argument will proceed similarly. So the spontaneous symmetry breaking doesn't really change anything in that regard.
Does it also not change the form of the statement?
Well, if your symmetry is spontaneously broken, you don't have probably a Fermi surface anymore. So it's a totally different emergent symmetry.
Yeah, I know.
Now, so
So
you will obtain a different result.
yeah. So I'm asking, what's the statement in that case?
Well, so the in a superfluid, the commutator of the this 2-pi flux basically becomes like a vortex in the theory. So the vortex has a translation symmetry commutator that's proportional to the superfluid density. So then it kind of just tells you that the microscopic density is equal to the superfluid density, which is maybe not very surprising. I mean, because we're talking about zero temperature here.
Thanks.
Question?
Yeah.
Does this new derivation of Luttinger theorem does it allow an easy generalization to 3D as well, or are you going to talk about it?
I'm not going to talk about it. I mean, it can be generalized to 3D. Easy is in the eye of the beholder. The statements get a bit more complicated. But anyway, I mean, it can be generalized to 3D.
Okay.
Regarding this algebra of the ends, is this the same as Kac-Moody algebra without the central extension?
I'm not sure what you mean by central extension. I mean, this is kind of a central extension, right? Because you know, the commutator being non-zero is a central extension of the loop group.
Okay.
I mean, it is a Kac-Moody algebra. That much is true.
And the coefficient here is the k of the the coefficient here is the k of the Kac-Moody algebra. So this is k equals 1.
I'm not familiar with what
In other words,
k, but
is it? There must be an argument that the coefficient there of that multiplies the 1 over 2 pi is quantized.
yeah, it is quantized. Yes. So yeah, that will be one of the parameters of the Kac-Moody. I don't know which one is called k.
And is it clear what determines its value from here?
I mean, from this Poisson bracket argument, for example. I mean, I don't know how to say it in an intuitive way, but mathematically, this Poisson bracket argument makes it clear what the coefficient is. So it's always 1 for a Fermi liquid.
It depends on the magnetic flux, right?
Yeah, I mean, for a fundamental flux, 2-pi flux, then it's 1. Otherwise, you multiply it by how many flux quantity you have.
Thank you.
I have another question.
Yeah.
Dominic. So this kind of works only for a closed Fermi surface, is it correct? Because if I have not a broken Fermi surface, but let's say your Fermi surface extend all the way through the Borean zone, one could imagine a very simple naive case that is just a stack of 1D system. Then you would derive the Luttinger volume in a different way, right? You would sort of follow the previous derivation for 1D system. I'm wondering.
Luttinger's theorem does hold in that case. So I'm not sure. It's still true. It turns out that even in that case, that if you do the same argument, you'll still find the translation commutator is proportional to the Fermi surface volume. So the argument goes through the same. You just have to be careful about doing this computation, but it's still proportional to Fermi surface volume.
So if I have a whole bunch of decoupled wire, I could still go for a Fermi surface description, right? But the translation along the y direction would just always be okay. Maybe it's too detailed, but the point is that even in that decoupled array of wire case, the formula still applies. That's what you're saying.
Yeah, I mean, both momenta still act non-trivially in that theory. So I mean, you still get the same formula.
Okay.
Although, yeah, no, I think that's true. Yeah.
Okay.
Okay, so where were we? Oh, yeah, I just have proven Luttinger's theorem. So yeah, any more questions on that? So okay, so this is what I just want to emphasize. Because the argument only used the emergent symmetry and the anomaly, then now we have a program to go beyond Fermi liquids. All we need to do is whatever our fancy exotic non-Fermi liquid state is, all we have to do is first identify its emergent symmetry group, then identify its anomaly, and then we do this UVI matching argument, and we'll obtain either Luttinger's theorem or some generalization of Luttinger's theorem. So this really gives us a toolbox to go, way beyond Fermi liquids now. Okay, I want to just review this UV-IR matching argument and say it in the maximal generality, although it's kind of just what I said already. Where am I? Yeah, so microscopically, we have, by assumption, a lattice translation symmetry and the charge conservation symmetry. So in the IR, we have some emergent symmetry group, and we know that the microscopic symmetries have to act in the IR theory. So it means that there has to be a map from the IR symmetries, map from the UV symmetries into the IR emergent symmetry group. Okay, and then we know that microscopically, the translations have this commutator of the presence of a 2-pi flux, as I mentioned. And then we need to work out what happens in the IR theory. So this GIR emergent symmetry can have a Hooft anomaly, which means that coupled to a background gauge fields, you have an non-conservation of charge, for example, or something like that. And in particular, a consequence of that anomaly will be that if you apply a background magnetic flux, that the GIR will act projectively. And then since you have this map from the microscopic symmetries into the GIR, you can now conclude from this projective action of GIR, because the microsymmetries embed into GIR, you can obtain the projective action of translations in the IR theory. It will be some phase factor. And then you just need to equate that with the microscopic filling, and so that will basically be, you just equate these two equations, and you get some relation between the microscopic filling U and some property of the IR theory. So that's basically the general argument.
So again, following my earlier questions, so if I want to consider a 3-dimensional case, do I place something like a magnetic monopole in the lattice?
You can think about it like that. Yeah, you place a magnetic monopole, and then translations will act on some funny way. But it's not projective anymore. It's like some, for people who know about this, it's like classified by an H3 group cohomology instead of H2. It's kind of hard to say in physical terms what that means. But anyway, mathematically, there's some anomalous action of the translations of that monopole.
I see.
Okay, so now indeed I'm going to go beyond Fermi liquids as I promised. So okay, let me talk about some non-Fermi liquid state which doesn't have any quasiparticles perhaps. We need to ask the first. Sorry, is that a question?
May I ask?
Yes.
Do you have any example the anomaly is not a perturbative local anomaly, they classified by Z-class, but some finite non-perturbative global anomaly? Any example related to this phenomenon?
Probably, like if you're emergent symmetry with some finite group, maybe. I mean, I think in that case, the anomalies are always global, right? I think that I can come up with examples like that, although yeah, I can't do it off the top of my head. But I think, for examples, that where the emergent symmetry is just some finite group.
Most example here, the U1 plays an important role. Is that right? The charge conservation.
Yes.
Okay.
So maybe in the IR would be like U1 times some finite group. I think that still has some global anomalies. Yeah, I'm not sure.
Thank you.
So okay, so the question I need to ask is, what is the emergent symmetry of a non-Fermi liquid that has no quasiparticles? So naively, maybe what you might have thought is that because this LU1 charge conserved at every point of the Fermi surface, you might have thought that this is associated with quasiparticles, and so now since quasiparticles doesn't exist, you may assume that the loop group symmetry, which is saying that charge is conserved at every point of a Fermi surface, would get broken down to just the global U1, so it's only the total charge that's conserved. But if you thought that that would be what happens, then you would in fact be incorrect. So it turns out that this is not what happens, and I will explain why. And so basically, we have this theorem, which is one of the key results of our paper. So we have this, because we have now this very general way to think about the relation between filling and the anomaly of the emergent symmetry group in the IR. Now we can reason about general statements about that. And in particular, what one can show is that if the filling is an irrational number, then the emergent symmetry group GIR cannot be a compact Lie group. So this mathematically is pretty easy to prove once you have this general framework of the UV-IR matching. And in particular, if you have some state which is compressible, that basically is saying that the filling can be continuously tuned, If you can continuously tune the filling, then I mean, you're going through infinitely many irrational numbers, so this theorem will apply. So in that case, if your system is compressible, then the emergent symmetry group cannot be a compact Lie group. Yeah, so that's one of the key results of the paper. Maybe I should ask if there's questions about that.
So does this theorem apply to a superfluid?
Maybe I should say the U1 should not be spontaneously broken. There are some other subtleties too about like the possibility of the system to have higher form symmetries, which are technically this theorem only works if your emergent symmetry is only 0 form. It doesn't work for higher form symmetry. Or at least we can't prove it. It may still be true, but at least if this U1 is not spontaneously broken. We know that if a U1 symmetry is spontaneously broken, superfluid has no restriction on its density. It can occur at any densities. So in that case, at least in the superfluid, this theorem does not apply. But certainly if U1 is not spontaneously broken, this theorem probably applies, and definitely applies if there's no higher form symmetries.
So both U1 and the translation symmetry should be preserved.
Yes. Actually, there's some funny examples if you break translations, if you have incommensurate density wave order, but that can also be associated with an irrational theorem. So yeah, we want both the translation and the U1 symmetries to be preserved.
Okay.
What's the commutator of the Hamiltonian with your symmetry n of theta? Does it commute with it?
Yeah, I mean, it's a symmetry, so it should be commute with the symmetries, that's correct.
And the momentum probably shifts theta.
Momentum does not shift theta. Because momentum is a translation in real space. In momentum space, it doesn't shift momentum, right? So the Hamiltonian commutes with momentum as well.
Okay, so the spectrum of the system should be in a representation of that symmetry group.
Yes, correct.
But the representations are infinite. So is there an infinite degeneracy?
Well, I mean, it's a gapless system, so I think in that case,
it should be an exact infinite degeneracy. The spectrum of the representation of this.
Sorry, the n of theta, at least without magnetic field, the n of theta is in abelian group. So actually, representations are one-dimensional.
The representation is infinite dimensional.
No, a representation of this n of theta group is an irreducible representation is one-dimensional. I think you're thinking about the case where you switch on a magnetic field, in which case you have a non-trivial commutator. But I'm talking about the case with no magnetic field. Then the n of theta is commute. It's an abelian group, so the irreps have to be one-dimensional.
No, I mean, if the n of theta is commute, there's a simple representation. But if the n of thetas do not commute, and you have this delta function on the right-hand side, delta prime, then the representations are infinite.
Yeah. So actually, in a magnetic field, the turns out the Hamiltonian doesn't commute with the n of thetas anymore. Maybe that's a subtlety.
Okay. So, but then I would ask another question. If it doesn't commute, the infinite dimensional representation, this algebra is not a symmetry algebra, it's a spectrum generating algebra. It generates an infinite dimensional spectrum, going higher up in energy. So at some point, your low energy approximation is no longer valid. So how far should we trust? How far in energy should we trust the symmetry algebra?
Well, I mean, it's two separate things. I mean, the symmetry algebra, I think, is fine. I mean, you're asking about the Hamiltonian, though. I mean, we know in a magnetic field that the Fermi liquid will form Landau levels and stuff. So, I mean, maybe this is the question you're asking about. I mean, it's exactly the same story for a 1D chiral fermion, right? I mean, a 1D chiral fermion also has this, this Catch-Moody algebra structure, and the Hamiltonian is like it moves the particles along some velocity and some spectrum.
Then it's not infinite dimensional.
Why is it not infinite dimensional?
I thought that the symmetry algebra, the 1D example, has finite dimensional representations. is in the 2D example.
Well, no, I mean, sorry, I'm talking, I don't know what, I mean, there's a 1D Luttinger liquid, which is a non-anomalous state. But then there's the state you get if you take a 2D Fermi liquid and apply a magnetic field in and say what happens near the Fermi surface, which is kind of like a 1D chiral fermion in momentum space. So that would have a, I mean, that would, you know, look very much the same as a 1D chiral fermion. So not a Luttinger liquid. Luttinger liquid, when I say Luttinger liquid, I mean a non-chiral Luttinger liquid. So you have a 1D chiral fermion, it would have this infinite spectrum structure, I guess.
Thank you.
Yeah, I have a question. Is this a loop group LU1 is a compact or non-compact Lie group?
Well, it's not a Lie group at all, actually, because it's not finite dimensional.
Oh, I see. So that is a, so this LU1 is an example of a non-compact?
It's not a Lie group. I mean, a Lie group by definition means finite dimensional. At least most definitions would say it that way. And it's not a Lie group.
So that would be example which is allowed by this irrational fielding fraction.
Yes, I mean, and indeed, I mean, we know this must be true. I mean, a Fermi liquid certainly must exist at arbitrary filling because you can put a Fermi surface whatever size you want.
Okay.
So you did mention a clear distinction between this LU1 and U1 to raise to infinite power. Is there a, are you going to talk about a clear physical difference in consequences of these symmetry groups?
Well, probably not. I mean, I mean, U1 infinity is not the right symmetry group. So I didn't really want to say much more about that. I mean, it would, and everything I say would like totally break down if the symmetry was U1 to infinity. But I don't know if I want to go too much into that.
GIR that you write here, does it contain already translations or not?
Yeah, GIR is all the emergent symmetries of the system. But the thing is that the translations, even though microscopically they translate in space, in the IR theory, because you've coarse-grained, you expect them to be internal, act effectively as internal symmetries. So GIR will contain all the emergent symmetries, or at least the emergent internal symmetries, but it turns out the momentum actually is an internal symmetry in the IR theory.
So if the symmetry is just translations and U1, this would be compact. You would say that this is a compact Lie group.
Well, if the symmetry was translations and just in U1, this is would not be a compact Lie group because Z is like an infinite group. So I mean,
yeah, but then wouldn't this statement always hold? Because GIR always contains inside it the translation.
No, the GIR does not need to be, even if microscopic, this is the emergent symmetry group in the IR. Even if microscopically you have a translation symmetry, it doesn't mean that you have to have a Z symmetry in the IR. Like, for if you think about this Luttinger liquid, for example, the emergent symmetry group is just U1 times U1. That's the compact Lie group. I should mention that this theorem is only true for spatial dimension greater than or equal to 2. That's why it doesn't apply to the Luttinger liquid. But in any case, the Luttinger liquid has a compact Lie group emergent symmetry U1 times U1, even though it has translations microscopically.
Oh, I see. Okay.
Yeah, I should have said in the slides, this theorem is true for D greater than 1, spatial dimension greater than 1. Right, so that's a very general statement. I mean, so going back to this non-Fermi liquid, I mean, it cannot be the case that the LU1 is just broken down to U1 because U1 is a compact Lie group. And if we believe that this non-Fermi liquid state is compressible, which probably should be, then that would be inconsistent with the theorem. So it's not the case that LU1 is broken down to U1. So what does happen? I mean, here we get a little bit more into the realm of speculation. It needs to have some emergent symmetry group that's larger than any compact Lie group in order to be consistent with the theorem. So we will have many, many conserved quantities. I think the easiest case to imagine would be just that the emergent symmetry structure would just be the same as a Fermi liquid, in fact. So even though you don't have quasiparticles, you still have a conserved charge associated with each point of the Fermi surface. It's just kind of not quasi-particle in nature. I think so. That's the scenario that we should probably imagine, that even though that you have these many conserved quantities associated with charge at each point of the Fermi surface, and but there's some dynamics going on at each point. It's not like just described by quasi-particles. So in that case, so the emergent symmetry group is still the same if that scenario holds, and so it's loop group still. And so I will call that, if that holds, I will call this an ersatz Fermi liquid. I mean, so it can certainly be very different from a Fermi liquid, but it has this particular feature in common with Fermi liquid that has the same emergent symmetry structure. So we call an ersatz Fermi liquid. There could be some interesting implications of this for dynamics, because we have always a very large number of emergent symmetries. So if you imagine some thermalization, which again could be quite rapid in a non-Fermi liquid state by contrast to a Fermi liquid state. But it has to thermize with some generalized Gibbs ensemble, because all these emergent symmetries are still conserved. And then once it does that locally, maybe you could have some generalized hydrodynamics associated with that. So that would be interesting to explore, but we haven't looked at that. But going back to this emergent symmetry structure, so what I kind of want to conjecture is that in fact all non-Fermi liquids are really ersatz Fermi liquids, which is to say that they have the same emergent symmetry structure. Well, I have to put this brackets or slight variance off, because there's easy ways to kind of construct counterexamples to a strict statement. Like you take some ersatz Fermi liquid and just add some extra degrees of freedom with their own emergent symmetry group. I mean, that's certainly allowed, but it's not really fundamentally changing the idea of ersatz Fermi liquid. It's just that you're adding some extra stuff. So what I kind of want to conjecture is that all non-Fermi liquids are really just ersatz Fermi liquid, possibly with some extra stuff. But if you forget about the extra stuff, then it turns out that ersatz Fermi liquids still satisfy Luttinger's theorem. And there's just one asterisk, because in this commutator you could have a different coefficient. The coefficient's quantized, but if you have a non-Fermi liquid, maybe it's a different integer. And if that's the case, then it will satisfy Luttinger's theorem, but with a rescaling factor because of this coefficient. There's actually a simple example of that, which is a spinful Fermi liquid. I mean, before I was to talk about spinless Fermi liquids to simplify, but if you talk about spinful Fermi liquids, it actually has m equals 2, because you can count the two spin components up and down. That's kind of a trivial way to get different m. But there's also more exotic ways to get m not equal to 1. That would be interesting to find. But anyway, so with these ersatz Fermi liquids, which are defined by this emergent symmetry structure, must satisfy Luttinger's theorem, maybe with this rescaling factor. And if you're worried about this like fractionalized Fermi liquid FL star, well, that's kind of an instance where you have like Fermi liquid, but just plus extra stuff. The extra stuff contributes like some filling 1/2 or something, because it comes from a topological order. So in general, if you have this variant of an ersatz Fermi liquid with extra stuff, maybe you have an offset to this theorem.
Excuse me?
Yeah.
Yeah, I want to make sure I understand this commutation relation. So this means this commutation relation is supposed to be a property of the ersatz Fermi liquid. In particular, it's not a property. It's not something like a property that holds only if you place a 2-pair flux background.
No, sorry. I mean, I didn't say here. This is the commutator in the presence of a 2-pi flux background. That's what I meant by this equation.
Okay, thanks.
Okay, so this is a very general statement. I mean, subject to this conjecture, it seems like you always have Luttinger's theorem for all non-Fermi liquids. So that's a very general statement, in fact. Where am I? Well, I think I'm running low of time. I wanted to present this anomaly equation for the 2D Fermi liquid.
Sorry, if you don't mind. Are there examples that you're aware of for non-Fermi liquids that satisfies the commutation relation with m not equal to 1?
Well, apart from the spinful case, which is kind of just doubling the spinless case, I don't know of any examples.
I think emergent fermion may also have some emergent discrete symmetry, get a lot of components, and so that may change the m.
Emergent fermion would generally be associated with gauge fields, right?
Yeah, so
I mean,
some discrete gauge field, then there's some non-trivial representation. I wonder whether that would be mechanism for have a larger M?
Well, I think for a Fermi surface, you want to actually be a U1 gauge field, because you don't want to, for a Fermi surface, you want to kind of have a U1 symmetry. So it would be a
There's
U1.
a global U1 symmetry, but there's a emergent fermion also in addition carry some discrete gauge.
Yes.
That symmetry you degeneracy and
see
M.
what you mean.
Yeah.
I mean, there the emergent symmetry is a bit more complicated, because you have to take into account that this discrete gauge field also has like one form symmetries. So
yeah.
The precise statement gets more complicated.
Okay.
So it's not just that you change the M, but okay, maybe in some effective sense you have fractional M once you like integrate out the gauge field. But yeah, I'm not sure exactly what the statement is.
What is the motivation for this conjecture? Like, if I have a critical boson interacting with the Fermi surface, the boson can change the momentum of my charges.
Well, so, I mean, yes. I mean, kind of a UV sense, that's true. But the question is whether you have some still emergent charge conservation associated with Fermi surface in the IR. So I mean, so that's basically what I claim would probably happen in that case. I mean, the motivation for the conjecture is that this theorem, right? I mean, we have to have some very larger than any compact Lie group emergent symmetry, assuming we're talking about a compressible state. So, I mean, if it's not this LU1, it has to be something else. I mean, maybe it could be something else, but that would be equally non-trivial. But the simplest case would be where it is just LU1. And so that's what I expect to happen, at least in some very large class of non-Fermi liquids. You can actually see in the fixed point theories that people have come up with to describe like fermions coupled to some capitalist boson or something like that. It actually does explicitly have this LU1 symmetry, although people perhaps don't use that language normally, but it actually does, at least in the emergent sense, have this charge conservation symmetry at each point of the Fermi surface.
This is some large N limit where you can actually analyze that system perturbatively, or what do you mean by studying the fixed point equations? Do you mean the like non-perturbative Schwinger-Dyson equation?
I'm not too familiar with the story, but I mean, you can come up with some fixed point theory. I mean, you don't know necessarily what the UV would have to be to flow to it, but there's some. I mean, okay, I'm showing the limits of my expertise in this area, but.
Can I just comment on that?
Yes.
So, so if you accept that the eventual fixed point in such a problem can be accessed through this patch description, where you split the Fermi surface into tiny patches. So that patch formulation, it's contained within that patch formulation that there's this emergent symmetry. So if you believe that patch formulation, then this emergent symmetry is just there.
Yeah, this is what I was attempting to get at. Yeah.
So I have a simple question. So where would the Dirac spin liquid fall into this classification?
The Dirac spin liquid.
Yeah, I mean, I have a Mott insulator.
That's a glass hole filling.
The interaction is so strong that I'm in a Mott insulator and I have a gabless.
Well, this is like a semi-metallic state, right? Not a metallic state.
No, yeah, but it's a non-Fermi liquid in a general sense.
Well, okay, I guess by non-Fermi liquid I mean like a metallic system. So a Dirac Fermi liquid, a Dirac spin liquid wouldn't exist at generic filling of the.
No, it's not even a metallic, but so your statement is restricted to conductor, so it has to be.
Well, it applies to any system where the charge filling can be tuned continuously. I expect that to be kind of synonymous with metallic states.
Okay. So any Mott insulator would fall outside of this.
Yes. I mean, you can still analyze the UV IR matching for that Mott insulator using this general framework that I did. And so it's interesting to think about that, for example, in the case where you have a spin-on Fermi surface.
Yeah.
We discussed that in the paper. But in terms of this conjecture, I'm not saying that this conjecture applies to that system.
Okay.
Okay, this is technical, so I better skip it. It's just, the point I just wanted to make is that you write down the anomaly equation for this loop group symmetry, which is some violation of continuity equation, as in the 1D case. It's this form, which is kind of a generalization of 1D formula, but to make this make sense, you need to introduce kind of an extra direction, which is the theta direction, the direction of the Fermi surface. So even though we have 2 space dimensions, 1 time direction, the direction on the Fermi surface becomes an extra dimension in which this anomaly equation holds. So the anomaly equation actually holds in a 4-dimensional space. That's kind of an interesting feature of these smooth groups. And so in particular, it kind of knows about the various phases on the Fermi surface. That's kind of that's a interesting feature of this anomaly. It actually knows about the Fermi surface various phases. And so there's actually a lot of interesting consequences of the anomaly equation. Luttinger's theorem, as I already mentioned, but there are other things you can deduce just from this anomaly equation, which remember is independent of the Hamiltonian, and it holds in any ersatz Fermi liquid. So electric field response, anomalous fault conductance, chiromagnetic effect, all of them just come directly from this anomaly equation. So it doesn't even matter what the Hamiltonian is. They're kind of topological properties, if you like. Okay, and this is my final slide. I just wanted to advertise some other things that I didn't get to. So we can understand quantum oscillations beyond Fermi liquids. Once you have this emergent symmetry structure, an anomaly, basically, that is enough to understand why you have quantum oscillations. So that allows us to generalize this theory of quantum oscillations, well beyond Fermi liquid theory, which is in agreement, I think, with what people see in experiments. You don't need a Fermi liquid to have quantum oscillations. And then we talk about some states that are not metallic in the conventional sense, so the half-field Landau level and the spin on Fermi surface. And we also show that Fermi arcs are impossible in these frameworks. So if you see it experimentally, Fermi arc, it's probably that you have a closed Fermi surface. It's just some of it is hidden from your probe. Yeah, okay, I think that's all that I wanted to say. I'll conclude there.
So thank you, Dominic. It was a super interesting talk. So given that we went over time, let's maybe just officially end the seminar here. I'll stop recording, and then anyone who has questions, just stick around and we can talk more.
Thank you very much.
Yes, thank you.
So does the Luttinger theorem, the framework developed here,